We're now going to move to including growth in our calculations. And to do that, we're going to consider an entirely new example. And so the results here are using different variables, and so we're going to end up with a different value. You'll also notice that I'm using Excel within Windows 8 for this example, and so the background and appearance is a little bit different depending on which computer you're using. Okay, we're going to be again using a 10-year DCF. We're going to be now using a growth of 5% and a yield of 7%. And we're going to be discounting that at a discount rate of 12%. We're still going to be beginning with our rent of $10,000. Once we start using growth, we start being even more critical with timing. And to illustrate that, we're going to start off by looking at what this rent means. We're saying that the rent is the present value rent. In other words, that's really the rent at the time that we acquire the property. And in the next 12 months, we'd expect that rent to grow with the annual growth rate, in this case 5%. When we capitalise to work out the value, we really should be capitalising not against the past year's rent, in this case the $10,000. To be precise, we really should be capitalising against the expected rent in the next 12 months, so that would be the year 1 rent. We'll illustrate that as we go along. Okay, to do it longhand, we'll begin by working out the rents. The first rent is going to be the rent that's going to be received in year 1. That's going to simply be equal to the rent in at present, last year, multiplied by the growth rate plus 1. That gives us $10,050. We'll leave that for the moment. We're going to work out the other rents shortly. But at this point, we can say that we really have the information now that we need to be able to capitalise the value. And so we'll come over now to the capitalised value. We'll do a simple capitalisation here in cell M52. And that's going to be equal to the expected rent for the coming year divided by the yield, in this case that's 7%, in cell F43. And that gives us $150,000. So that's the simple way to analyse this property. Let's continue with our DCF now. We come back and we say, what's the rent going to be in year 2? In year 2, it's going to be the previous year's rent multiplied by 1 plus the growth, which is 5%, close brackets. That gives us $11,025. Now, in that form, the equation's working, but in order to fill it across, I'm going to have to make sure that it catches the growth rate constantly rather than moving out. So I'm going to have to make F41 absolute. So I'll hit the F4 key, working Windows, and now I should be able to grow that across my 10 years. Now you'll notice I'm actually also wanting to grow it out to year 11. That's going to become very important, not because I intend to earn that rent, but I need that in order to compute the notional sale at the end of the analysis period. I can't capitalise off the year 10 rent, because remember, the value is the value from the rent that's anticipated in the year following the year of sale. So it pushes us out to year 11. Now you'll notice in the earlier examples I didn't bother to go out to year 11 because the rents were all the same. We didn't have any growth. We didn't need to do that. So there's a little approximation in there that didn't make any mathematical difference. It just made our model look a little tiny bit tidier. But here we have to be a bit more precise. Let's do that capitalisation. It's equal to the rent in the year following the year of sale divided by the cap rate. And so it means that in year 10 we're going to be selling the property for $244,000. Okay, we come back and we put in our discount factors the same way that we did before, and that's equal to 1 plus the discount rate raised to the negative year number. And again, if I absolute the discount rate by hitting the F4 key, I'm now able to fill that across. If I don't hit the F4 key there, you'll find that my discount rates very soon become something a bit absurd. To work out my PVs, again, it's the future value multiplied by the discount factor. I can fill that equation across. There's no absolutes needed. Now over here, I'm actually going to have to change this equation to take account of the fact that I've got the notional sale as well, so I'm just going to add that in. It's easier to do it this way than write the whole equation out by hand. A sign of my inherent laziness. Now we come back, sum all of the PVs of the annual cash flows, see what that equals. Oh, it equals $150,000. Isn't that nice? So once again, even though I'm now considering growth, by the time I carefully put growth in, and that means carefully consider what cash flows, which rentals I capitalize for the capped value, and also how I manage growth across the analysis period in the DCF, I still end up with the same result. So is capitalization better or worse than DCF? Well, the debate continues. However, this is a fairly long and cumbersome way to do DCF analysis. And you can see that there's certainly a computational advantage in terms of doing the capitalization. However, we can also use the built-in Excel functions to simplify this down to just a handful of equations. But to do that, we're going to have to do one intermediate step. And that is, it works on noting the similarity in the mathematics between what happens when we're doing the growth, which is 1 plus the growth rate being multiplied, and what happens when we do the discounting, which is 1 plus the discount rate being divided. The minus exponent there turns it into the reciprocal, which is a division, for those of you who remember your high school algebra. And so it means that we're doing 1 plus something raised to a power, divided by 1 plus something else raised to the same power. And so there's a kind of a similarity there. We're growing in one sense and we're discounting in the other. Now we can roll that all into a single calculation by using what we're calling in this course, or this program, the compound discount rate. Compound discount rate is what happens when you roll together the discount rate and the growth. The expression for the compound discount rate is here in red. The compound discount rate is 1 plus the discount rate divided by 1 plus the growth rate minus 1. Let's calculate that. That's going to be equal to, open brackets, 1 plus the 12% in J43 divided by, open brackets, 1 plus the growth rate, which is 5% in cell F41, minus 1. You'll notice the yellow highlights are disappearing to tell me that I'm getting the right solution. So what that means is that the overall effect, if I've got some value like the payment, the net rental, and it's growing at 5%, but I'm also discounting it at 12%, that's the same as simply discounting it by the 6.67%. That's kind of nice because it's easier to use this compound discount rate because then I don't have to grow and discount. It's all done in one function. Let's look at how that works with the rents. What I can do here now is use the Excel PV function where the rate is the 6.67%. The number of periods is 10. Now for convenience I'm just going to pilfer the 10 from M45. It's not probably the best place to get it from, but it's there. Now the payments here. Now this is important. If you get this, it'll make the rest of the course a lot easier. Remember, we're using this compound discount rate. What that means is, for those of you who are mathematically inclined, what we are doing is growing everything from time 0, the present, and we're also discounting it. Now, to do that, we have to work with the present value of the rent. In this case, it's laid out so it's really easy. It's the $10,000. However, in other cases, especially in practice, you might have to give a bit of thought as to what your starting rental is going to be. Was last year's a reasonable amount to take? Do you have a reasonable estimate for the next year's? It's a matter of looking at the data, but you've got to be on the ball with this one because it's easy to make a mistake. And really, if you're working at a growth of 5 or 6%, that's exactly the percentage of error that you're going to put into your answer if you choose the wrong one. Okay, we're going to use a negative sign here to keep in harmony with Excel sign conventions. And if all that is correct, then the yellow highlight goes out. So I've got $71,330. And Excel is telling me that that's the right answer for that cell. That's nice. What that's telling me is that if I simply take the net present value of the sum of rents, these 10 values along here, and simply add those up after they've been PV'd, that's without the notional sale, I get $71,330.93 and so on. We can now do the notional sale. I'm going to use the same mathematics or the same function to do that, but there are actually a number of ways of computing it. You can grow it from the capped initial value. We're just going to use the built-in Excel function. Kind of has a nice form to it. That's going to equal to PV, so it's the same form. The rate is going to be the discounted, so the compound discount rate, comma, number of periods is still going to be 10. Here I don't have a payment, so I'm going to do 2 commas to get past the payment parameter input. Now we're looking for the future value, and the future value is going to be, again, the initial capitalized value because we're going to be using the compound discount rate, so we're going to be growing it and then discounting it, all using this compound amount. So the end value is actually the starting value, again, because the compound discount rate does the growth and discounting all in one step. Long and short of it is we choose the rent in year 1, which we then divide by the yield. We'll put a minus sign in there for Excel sign conventions, close brackets, and that means that the present value of the notional sale in 10 years' time, okay, the dollar value is still going to be $244,000. However, we've calculated the present value of that and its grown amount from the initial capitalization, all in one step, as $78,669. From there, we can very simply add these together, and so 71,000 plus 78,000 and bits and pieces, again gives us 150,000, and so once more we come up with the same value. So we can see whether we use the capitalization approach or the longhand DCF or the compound DCF, we are doing the same mathematics. We're getting the same result. In practice, we may not find it quite so elegant because there are more complex factors giving us the payment or the net rent. However, it illustrates that we can use either of these 3 approaches. The advantage of the discounted approach, of course, is that eventually we'll be putting more complexity into the net payment amount and perhaps other values as well. So it gives us more flexibility and precision there. But the real point here is that by using the compact mathematical approach, the compact built-in functions, we're able to get the entire result in 3 equations rather than a whole tablecloth full of calculations running across the spreadsheet. So this is obviously a far tidier and faster way to do your analysis. Now, for those of you who are a bit perceptive, you'll notice that these 2 equations in cells C56 and C57 are very, very similar. And in fact, in one of them we use the payment and not the FV, and the other one we use the FV and not the payment. And so for those students who like a little bit of a challenge, I'd recommend that you see if you can actually get this down, instead of 3 equations, get it down to 1 by writing one Excel equation which gets the PV of the rents and the PV of the notional sale, and will give you that $150,000 immediately without doing this two-step approach. So we'll consider that an extension activity for you. What we can see overall with all of this modelling we've been doing is that there is a very strong mathematical connection between the calculations using capitalisation and the mathematics using DCF. Further on, of course, we're going to find that the advantage of the DCF is that we're able to put a lot more considerations into the DCF. The capitalisation value does have a lot of assumptions built into it, and that's why it's so simple. The examples we've used here are rather sanitised. We're assuming that growth is constant and so on. We're assuming that yield is constant at the beginning and the end of the analysis period. Now, both of those assumptions don't really hold in the real world. By the time you get a building which is an extra 10 years old, you're going to find it's a little bit closer to its use by date, so its yield will probably rise a little bit. And if we're doing a 20 or a 30-year DCF, that certainly will be the case. Nice thing about the DCF, though, we have got the confidence that we're using the same mathematics, and so as we put more and more detail into our model, we know that while we're conceptually doing the same thing, we're able to get perhaps closer to the real world, or at least as close as we can. Good. Generally, in this course, we're going to be using the compact DCF approach more and more, in fact, almost exclusively. And so go over these exercises, make sure that you're on top of these simple ones, so that when you dive into the more complex ones, especially when you get into pastoral interests, you're able to do it without being fazed by it. One last point which is worth taking away from this is the relationship between growth, yield and discount rate. Often people get confused as to whether the cap rate is really another name for the discount rate. However, it really comes down to the fact that growth plus yield give you the total return on any investment. And here we see that the growth rate of 5% plus the yield of 7% gives us about the discount rate of 12%. Now, is that going to be a precise relationship all the time? Well, it tends not to be, but it tends to be approximately the case. And so your discount rate, which is really your total rate of return, is typically approximately the sum of the expected growth rate plus the expected yield.